Hello again. We're going to look at the half-life of a radioactive isotope. And what I want you to think about during this video is not only the calculation, but what this means. So the half-life, or T1 half, of a radioactive isotope is the time it takes for a half of the sample to decay. This is a very big issue when we're dealing with radioactive and nuclear chemistry. So when we are using nuclear power, nuclear reactions, nuclear um, bombs, nuclear power, um, all sorts of things, we are generating nuclear waste, which means we're generating waste that has radioactivity. And how do we get rid of this waste? How do we store it? And that's a huge debate, huge problem, because a lot of these radioactive isotopes, they take thousands of years to decay, and therefore they are potentially dangerous. We haven't talked too much about that at this point, but radioactive isotopes, a lot of these isotopes can be very dangerous. So anything that emits gamma rays can completely penetrate your skin. Like, you have to have protection from these rays. It can only Gamma rays can only be stopped with like a concrete or a lead wall. Okay, and so these are very dangerous. They can be very useful, and so there's ways that chemists have found to make these very useful to us. When you go get a stress test at the hospital, you're ingesting a radioactive isotope that they have now found that will not get into your bloodstream, and if it did, then you would die. But it just you easily pass it through you, and therefore it can go through, and you can get the images and things that you want. But what do we do with this waste? And so think about that while we're going through this. So if we have 16 grams of P32, the isotope phosphorus 32, and its half-life is 14 days. Okay, so each radioactive isotope is a property, this half-life is a property of it. So different isotopes have different half-lives. Okay, and it doesn't matter the amount of the sample, the temperature, the pressure, and this is actually sort of a negative when we're thinking about trying to store this radioactive waste, because it doesn't really matter what we do to it. We can't, make, drop or raise the temperature, or change the pressure or anything like that to change its half-life. If it has a half-life of 1,000 years, that's its half-life. We can't do anything about that, okay? And so P32 has a half-life of 14 days, okay? But it's so different. So if you look, I meant to show that, sorry. The half-life is a property of an isotope. So here's just a few isotopes, common radioisotopes, and their half-life. So look at carbon-14. Its half-life is 5,730 years. Okay, cobalt, 5.3 years. Iodine, 131, is 8 days. Huge difference. So we can use these. So we use it for thyroid therapy or cancer therapy. Potassium 40. Okay, look at its half-life. 1.3 times 10 to the ninth years. It's hard to even fathom how long that is. Phosphorus 32, 14.3 days, so not that long. Technetium 99, okay? This is used for organ imaging, okay, because it passes through and its half-life is short. It's 6 hours, okay? So we can joke that we're radioactive for 6 hours or more, because that's just the half-life, right? But, within 24 hours or so, it's through your system. Okay, we couldn't use that, necessarily in our bodies or whatever, if it had much higher half-life. Okay, uranium 235, really long half-life there. Okay, and this is used in nuclear reactors. Okay, so half-life is just how long it takes for half of it to be gone or to decay, not all of it. So if the half-life of iodine 131 is 8 days, how much of a 100 milligram sample would remain after 32 days? Okay, so there's really two ways to ask you these problems, and I'm going to go over both. But here we have 32 days, and our half-life is 8. So we need to just figure out how many half-lives are we going to go through in 32 days. Well, 8 into 32, right, is 4. So we have 4 half-lives. Okay, so if you think about it, you're cutting that amount in half 4 times. Okay, so you have 100 milligrams, so you could say 100 divided by 2, divided by 2, divided by 2, divided by 2, because you have 4 half-lives. Okay, so you could take that 100 milligrams, that initial mass, divided by 2. That's what I do in my calculator. I divide by 2, divide by 2, divide by 2, divide by 2. You divide by 2 4 times because you have 4 half-lives. So after 4 half-lives, or 32 days, you would have 6.25 milligrams remaining. They use this in carbon dating. You may have noticed that on the chart earlier. It has a carbon-14 has a half-life of 5,730 years, very long time. But what they can do is so that they can take the ratio of a radioactive carbon-14 stable and look at the ratio between carbon-14 and the stable carbon-12. See, carbon-12 is not radioactive, doesn't decay or spontaneously emit radioactive particles. So they can compare these two. So once an organism dies, they can use this radioactive carbon dating to determine how long something has been deceased. So they, after the organism dies, the carbon-14 decays, and it's not replenished. But then there's still that carbon-12, so they can look at the ratio between these two and determine the age of the artifact. Okay, so that's a pretty neat way to use this half-life. All right, let's do a couple of practice problems. So there's two ways you could be asked. So I have an A and a B here. We have cobalt-60, and it has a half-life of 5.25 years. That's what it is. That's its half-life. Okay, and if we have 2.65 grams of it, we want to know how much do we have after 3 half-lives. Okay, so this one gave you how many half-lives. So we're going to divide by 2 or 1/2, however you want to do it. Same thing, divide by 2, divide by, and divide again. So get your calculator out. Take 2.65 divided by 2, divided by 2, and divided by 2. Okay, so you're going to get 0.331 grams of cobalt-60 remaining. Problem B says after 21 years. Okay, so now we need to figure out how many half-lives we have. So 21 divided by 5.25 is 4. So we have 4 half-lives. So we're going to take 2.65 grams and we're going to divide by 2, or 1/2, whatever, doesn't matter, divide by put that for the half-life. We're going to divide by it 4 times. So take your calculator, put 2.65 divided by 2, divided by 2, divided by 2, divided by 2. So I divided by 2 4 times, and so I have 0.166 grams remaining after 21 years. All right, I hope this helps, and I'll see you soon.